Okay, hi, this is Michael again. We're back and we're showing how to do a demo of the force plate. So the first thing we're going to do is we're going to demonstrate the calibration. And this is just pressing on it to see which is which. That's force 1 back there. And this is force 3, so it's 1, 2, and 3. And before we set this up here, I'm going to go ahead and put each of them, I'm going to scoot to the 50 Newton range. So let's go ahead and there's a switch on all 3 sensors that I've moved to the 50 Newton range. And now let's, yeah, that's still 1. This is still 2. And this is still 3. Okay, so let's go ahead and try calibrating them now. You go to experiment, calibrate, 1 dual range force sensor. And now we've got 200 gram masses that I'm going to set on them for the calibration. So let's go ahead and calibrate now. And 0 with nothing on it. And then 200 grams, if you do the math on that, that's 1.96 newtons. Let's try that again, just make sure it works. 0, and then 1.96, keep, and now we'll go ahead and calibrate 2, 0, keep, and now let's go ahead and put the 200 grams, this is 1.96 newtons. Let me try that again. 0. I'm not sure that hitting return is the same as hitting keep, so I'm going to just hit keep instead. Alright, now I'll select the third one. Calibrate now. 0. Put the mass on it. 1.96 newtons, keep, and then done. So now 3, we've got the mass on it, 1.96 newtons, double check 2, 1.96 newtons, and double check 1, 1.96 newtons. Alright, everything's copacetic with the calibration of the force plate. Now let's put the top plate back on, and in a perfect world I'd actually fire a rocket motor, and y'all can see that. That's real exciting, but it's not exactly a perfect world insofar as sometimes circumstances don't permit firing a rocket motor within the time frame that I wanted to get the video posted. So let's not worry about that too much, but what we've got here is I've set up fishing line between 2 fish hooks. So my plan is to measure the breaking strength of the fishing line by pulling down on the force plate, and it's a force measurement, much like a rocket motor when it gets fired. But this is an experimental technique that we use to compare the breaking strength of fishing line with its what it was rated by the company. Alright, that made the fishing line. This is it's the Yozuri HD carbon, and it's rated for 15 pounds. Alright, so let's go ahead and zero things out. Takes a minute to zero. Now let's go ahead and we'll collect the sweep just to see. how that behaves, and then we'll look at the statistics. Alright, now if we you could click on stats, look at the stats for 1, 2, and 3, and the mean is 0.00 something for all three, so we're very well zeroed out here, so that makes us feel good about it. Now let's do something else. Let's go ahead and let's try our heavier calibration weight, and this one has started in some earlier videos. We know that this is 21.685 newtons. So now we're just hanging it from the fishing line. And now we're going ahead and we're scanning. So this is measuring a constant force, and the force plate is pushing down on the 3 force sensors. And now if we add them all together, let's go ahead and click the stats, get the stats up. And so we could actually get a Windows calculator up here. So the mean of force 1 is 6.658, and then we add that to the mean of force 2, which is 5.752, and then we add that to the mean of force 3, which is 9.843. So in a perfect world, our cal weight would have been 21.685, but what we see is that it's actually 22.253. So I'm going to go ahead and we're going to save this, and I'm going to call this, let's go ahead and go over to our Vernier directory. I'm going to call it line break calibration, and I'm going to call it 22.253, because that was the total Alright, line break cal 22.253 is just what I'm naming the file. And now we're going to go ahead and do the experiment while we break the line. So let me go ahead and take a minute and just double check that everything is in view that you're going to need to see. Alright, you can see the force plate, you can see the top fish hook at least. I'm going to be pulling down on the bottom one, and you can see the forces in the line as it scans across. So let's go ahead and run this experiment. And usually we like a little countdown. I'm going to go 3, 2, 1, 0, start. And then once I see it started, go ahead and pull down and break the line. And you can see that it recorded the event nicely. And had we had a rocket motor sitting on there, and had we fired the rocket motor, it would have caught that as well. So let's go ahead and let's save this as, and we're going to call this line break T1 for test 1. And we're not going to sit here and do this over and over again, but if we were really doing a careful experiment, we'd probably do some sample size, maybe break 5 samples of the same fishing line, maybe 10, and then we would average the events and say have the peak breaking strength of the different lines. Alright, so now we need to zoom in a little bit, and let's first try zooming in. It looks like things happen between 2 and 3. So let's go ahead and just go from 2 to 3, because I'm also going to demo a little bit about how to start looking at the data, how to analyze the data, and so on. So most of the event here is between 2.2 and 2.4, and you'll notice that when I highlight that, And I'm going to go ahead and zoom in so you can really see what's happening now, since most of the rest of this is going to be on the screen. Alright, so highlight this, and if you come over here and you select copy, it copies the table elements that are highlighted into the clipboard. And then if you come over here to say a spreadsheet, you can simply paste them into a spreadsheet, and it knows that the tab delimited data is the different columns in the spreadsheet, so we'll go ahead and do that. And let's go ahead and we'll make our column headings here. So this is the time in seconds, and this column heading is force 1 in newtons, this one's force 2 in newtons, and this one's force 3 in newtons. Alright, now let's make this column here, let's call it raw total force, and that's going to also be in newtons. And why don't we go just call it F. And the reason I'm calling this one raw is because we're going to use the difference here in a minute between the calibration weight and what it measured when we were calibrating it, and we're going to have another column here in a minute that's going to be the calibrated total force, which is corrected for what we discovered with the calibration weight. Alright, so this is simply going to be the sum of columns B, C, and D. So sum, let's just do it this way. Let's just do B2 plus C2 plus D2. Alright, and let's go ahead and Control C copies that. And let's go ahead and Control V paste that. And actually we were probably sampling a little slow. Seems like we were only sampling at 50 samples per second, which is fine for the demo, but if we were doing this for real, we probably would have wanted to sample at 1,000 samples per second. So in a perfect world, we would have set our experiment. We were real careful about our calibration, but we weren't so careful about our collection rate, and maybe we could have increased the collection rate to 1,000 samples per second. Alright, so, but it's not too inconvenient to have fewer columns to deal with in the data file. So let's go ahead, that's the raw, and let's go ahead and then we'll make the calibrated. So let's just go total force. And this is the one that's adjusted for the calibration. Now let's ask ourselves this question. We wanted to, in a perfect world, we would have measured 26.685, but what we actually measured was 22 and change. So what we want to do is we want to multiply by what we actually measured. And let's go back over to the Vernier directory to remind ourselves what we actually measured. 22.253 is what we actually measured. So 22.253 times the raw total force, which is element E2, and then divided by what we should have measured in a perfect world, 21.685. Now let's think about this for a minute. Did we do that right? Because if we really measure something, if E2 was 21.685, then we'd want the real answer to be 21.685. But here we see that we have it backwards. So let's go ahead and make sure 22.253 goes in the denominator. $22.253 goes in the denominator, and then in the numerator we want to put equals B2 times 21.685. So now let's ask ourselves, if we hang, let's ask ourselves this question. If we hang the real weight, and the real weight is 21.685, then it's going to think that's 22.253. So if this is what the total force was, B2 would be 22.253. Those would cancel out, and then it would read what we know it really is, the 21.685. So when you're doing the calibration, it's the total force times what you know the actual weight you used to calibrate it is, and then divided by what the system measured when you did your calibration. Alright. So then we cut and paste all the other elements. So now we have a column which is the raw total force, and then we have a column which is the actual total force. Hang on. Shouldn't be column B. What am I thinking? How am I looking at the numbers and they're all wrong? It should be column E because we're multiplying the total force times the calibration factors. Right? So now essentially each number gets reduced by just a little bit. So 43 becomes 42 and change. 13.5 becomes 13.2, and so on. So that's a very reasonable result after our calibration. Okay, the other thing that I was asked to demonstrate is connecting the rocket motor to the actual force plate itself, and here's the force plate. And what we have is we have just a bolt. It's a 1/4 inch bolt coming up out of the force plate and rigidly attached, so that whatever we rigidly attach to the bolt is also rigidly attached to the force plate. So this is an example rocket motor, and we use a hose clamp because a hose clamp is made of metal and can grab it rather firmly, and there's no give like there might be with tape or tying it with a string or maybe wrapping a rubber band around it. We really want a rigid connection, so that's why we use the hose clamp. And so we just have a proper size nut driver here and put the hose clamp on it and just tighten it down so it's good and tight. You don't want it overly tight so that the hose clamp actually deforms the shape of the rocket. You want it firm enough to transmit the force very rigidly to the force plate, but you don't want to tighten it down so much that it crushes the rocket motor body. And that's all there is to attaching the rocket motor to the force plate. Maybe give you some different perspectives there to see how that really works and looks once it's done. So you can get those metal hose clamps just at any hardware store.